So, hi, I'm Bikram, as Dennis said, from Helvetia in Switzerland, an international company with about 15,000 employees worldwide. I've been building large-scale, high-performant enterprise platforms for telecom with Erlang for about a decade before I joined Helvetia in mid-2022 and switched to Elixir professionally. In our GitOps on Steroid talks last year at ElixirConf, we talked about creation of a generic state machine-based GitOps framework in Elixir to build various provisioning automation platforms. Now, in this talk, I will show how we upgraded our existing Elixir Kafka self-service to orchestrate a large-scale, semi-automated migration of Kafka cluster resources from self-hosted to Confluent Cloud. Now, all of the migration activities of a Kafka infrastructure does not involve Elixir. So after a short overview of our migration plan, I will dive into how we explored the power of Elixir and its awesome open source ecosystem to solve quite a few non-trivial challenges during our 1.5 year of migration journey. So in short, who we are. In Helvetia, I'm from a Helvetia integration platform team. What we do is we are integration specialists. We use GitOps, REST, infrastructure as a code to decentralized cloud resource management by implementing various self-services and automations and provides. We also enforce a governance and corporate policy checks. So it's all part of the different platforms we build. Now, before I get into the whole migration, I would like to go over a few terms that I'll be using in this presentation. So first up, Streamzy. It's a Kubernetes operator to run an Apache Kafka cluster. Now, service accounts and Kafka users are a cloud resource to manage access of a producer or a consumer to a Kafka cluster or topics in it. An application is a way of grouping these service accounts and topics by business domain or within the scope of different application microservices at Helvetia. ACLs or access control lists are defined between Kafka clusters and service account to grant or deny, read, write, delete permissions to clusters or topics in it. Now, Streamzy and Confluent, they do not have the same style of defining a resource. Hence, we cannot just use the definition that we had for Streamzy, so we needed to come up with a format that we could generically define a resource, whether it is a service account or topic, and we call them meta models. The goal of defining of this resource was we can take this meta model and then transform them to provision both Streamzy and Confluent Cloud at the same time to support the migration. I will show you some example later on of how that looked like. Now, this presentation is about the scale. Now, what is our scale? From the data plane at Helvetia, we have about 2 billion Kafka messages going back and forth per day, which boils down to about 500 bytes per message, and which then is 5 megabytes per second of throughput. From the throughput graph right here, you see that we have some throughput spikes. So the traffic is not very predictable, but we need to be flexible and adaptive to those traffic as well, which is then taken care of the cluster themselves, which is not really relevant in this presentation. Now, the more important part is the control plane here. As you see that we have a lot of applications, about 200, which then defines 500 different service accounts in them, 2,000 topics, 5,000 access control list per cluster. And then we have 3 clusters, one for every deployment phases like development, integration, and production. Changes in the control plane as well, if you see in this graph here, is also quite unpredictable. Sometimes we have a lot of spikes, sometimes less, and we are very automatically responding to such changes and migrating them into the provisioning system into the cluster. Now, our migrations and goals. At a very high level, we had to do only 2 migrations. Convert the Streamzy format of definitions into meta model, and convert the self-hosted Kafka cloud and all resources in it and migrate them into Confluent Cloud. To minimize the risk of potential loss of business due to platform outage or data loss, and then there is also coordination complexity of all of this, we decided against one big single-shot big bang migration. Instead, we decided to go migrate in waves. Now this gave us every step a little bit reversible, so it's not a complete rollback, but you can quickly fix problems as you go forward. Gave a minimum user impact, and gave the user a very good flexibility to choose when they want to migrate, when they are migration ready. As it turned out, a migration over a long period of time in a large organization, such as Helvetia, is usually not quite straightforward. We had to migrate a few other things in the meantime, which overlapped with our migration plan, but this we cannot avoid because they were decided organization-wide. Two of those additional migrations we need to do is to move all our streams and resource definitions from Bitbucket to GitHub, and also move the self-hosted OpenShift to Red Hat OpenShift service on AWS, which is otherwise called ROSA. Now, with taking all of this together, our final migration planned execution looked like the following. In the last quarter of 2022, we started migrating the streams definition into meta model, while at the same time, we also built a POC to evaluate the viability of provisioning Confluent Cloud to our self-service. Then we actually finished our self-service to start to provision the Confluent Cloud. Around that time, we were then ready to migrate our users. So in mid-2023, we started migrating our users to Confluent Cloud, which lasted till the end of the year. And then, in the meantime, the old resources were getting freed. They were not necessary anymore. To reduce cost, we started to decommission them. And finally, we ended up with the code cleanup. Since we have been reusing Elixir component at different stages, so it gave us the flexibility of doing some work in parallel concurrently. So we managed to save some time for the other two migrations which are not related to Kafka infrastructure migration. So I spoke about the meta model. So here is an example of how our meta model looks like. So on the right side, you have an example of a Streamzy meta model, a Streamzy model, which is a little bit more verbose. But the one key thing to notice here is we had 3 copies of the same definition format for each and every deployment stage. So we got 3 definition duplication. So our new meta model, we not only transformed the field by field information, preserved all the organization requirement of configuration flexibility, we also combined them into one stage or one definition for all stages together. Now, we did the same for the user definition. So we also could also reduce the volume of the definition that you maintain in repository. This meta model definition, though it's very user-friendly, very lightweight, streamlined, we had some challenges to actually do it right. So at a very high level, our architecture of migration was the following. So we read every definition from every branch of the repository. So one from devel, int, and prod, we transform them into meta model, the simple Elixir script. We merge them together, and then we write the new meta model definition in the meta resource definitions. It was not as simple as that. We had a lot of conflicts and anomalies. Since the original definition we maintained in 2 separate GitHub branches, the users were starting to diverge in their decision of what the changes are. So we came into a lot of merge conflicts and so on and so forth. But we needed to clean it up since we can have only one meta model for all stages. So this ended up being a little bit more complex, but this is basically the internals of our migration script. As you can see, the complexity arises from not only from the volume, but also the interrelationship of them. At a very high level, the red lines are the final product of migration, whereas in the blue lines, we needed to do a lot of intervention, debugging, and checks, so it created a lot of intermediate results to actually be able to compare if the migration is going correctly or not. The migration script itself was about 1,000 lines of a single mix script. We heavily used the Git CLI Elixir repository and the JSON and JSON schema projects to interact with the repositories and the branches, and then parse the JSON definition, validate with the schema, and then migrate. We implemented our own logger custom backend to pick up the logs that this migration script is being generating through the migration cycle and write that into an XLX report. During the migration, we ran into these conflicts that I talked about before. So here's an example of such a report that we created in the meantime, where in the action it says fix in legacy, which means now this report is then analyzed by our Kafka experts. He finds out the way how to define this correctly in the source, and then you run this migration again and generate another version of the report. We had to roll our own YAML writer because, as you know, the JSON maps have unordered keys. So in order to have the migration, the meta model look nicely in the file, we needed to write one for our own. The script itself was designed in a way that it was easy to extend and also intercept and handle different exceptions. The average execution time of these scripts to migrate the whole bunch of our all Helvetia definitions was around 2 minutes. As for the POC, we managed to build it with the components that you already built for migration script fairly quickly. We took a few service account meta model definitions and topics and turned them into a Terraform script through our addition of some new models in the Kafka self-service. And then we used Confluent provider, Terraform provider, to actually provision them into Confluent Cloud. This POC we demonstrated to our steering committee successfully at the end of December 2022, and we received our budget approval and go ahead to actually start our migration. From that POC, we needed to do a little bit more work to actually make it ready, the self-service ready to handle migration. So the first thing we did is we upgraded our self-service to use the Git state machine-based self-service model that we presented last year. There is a link if you like to watch our presentation from last year. We used heavily EX templating to generate the Terraform script from the meta models. We improved a lot on the performance by building these transitions and combinations and all of that using task async concurrency. We used quite a bit of meta programming to reduce code complexity and duplication. And as for handling the data throughout the pipeline in the lifecycle inside self-service, we used Elixir structures like this, which gave us a clean, simpler, and type-checked code. Now, there is a small caveat about using task async, which I ran into, I had a nested task async, and then at the top level task async had timeout infinity, but the inner ones did not. So when the inner ones did timeout, the error message was extremely hard to understand and find out where we went wrong. So something good to take home with. All right, so here's two small examples of how our EX templates look like for the generation of Terraform. So we receive a list of service account structures, and you access those fields to fill in a Terraform template for service account, and same we did for topics. Of course, there are more parts to this Terraform script. It's not this small. So we also had to build resources for roles and access control list, but they more or less looks like this. The second point was the metaprogramming. Now, we did a few metaprogrammings, but this one is my favorite. So we have these governance checks. A part of our self-service is designed to actually check what user is trying to change is valid. And these governance checks are just simple business logic, right? So there is not too much Elixir going on about it. And we wanted to make the definition of governance checks quite user-friendly so that someone with little Elixir knowledge can read, understand, and document and all that. So with this sweet little macro, we came up with an annotation called rule, where you could write what this governance checks is about. And then you write a simple Elixir module like this. The macro would then collect all the rules and the function names around it, turn them into a documentation, and collect the function names and exposes them with the rule function below, which then with the 3 lines of code integrates easily into our self-service framework. This was quite successful because I know one of my Kafka expert colleagues decided to contribute because he says, oh, easy, this is easy, I can do this. So I was quite happy, and he did not have a lot of Elixir experience. So this was one success, and we actually reused this pattern in another place as well, reducing code complexity and duplication. With all of these building blocks in place, now we build these pieces of self-service. So this may look a bit complex, but this is nothing. It's the tip of the iceberg. It's actually way more complex than this. At a very high level, we got the topics and service accounts in meta model. For every stage, we run an independent Kubernetes pod to read the definition, filter them for the stage that this particular service is going to provision, convert this into the Terraform script of 2 kinds, one for service account and one for topic definitions, and then use Terraform Cloud to actually provision them into the cloud. In the same process, the 2 red lines, 2 red arrows, during the provision into Terraform, into Confluent Cloud, we generate some configuration information and some access credentials and stuff. Our users do not have direct access to Terraform Cloud, so we copy them out also through the same script and into Kubernetes OpenShift namespaces where every application user has access to. Now, a migration means that you need to maintain 2 things at the same time until it is over, right? So here comes the lower part of it, that the same meta model which we migrated, then you build a reverse migration to Streamzy so that you can actually keep provisioning the old infrastructure and keep them at the same level at all time. Right, so all of this we finished by the first quarter of 2023, and then came the big part of how we now migrate our users. So a very high level of a Kafka migration would go something like this. In a very simplistic way, you got a topic, someone is producing into the topic, and someone is consuming from it. So during the migration phase, where you're migrating the entire Kafka cluster from one cloud to another, you create something called a real-time mirror. So this is not one of the components that I'm not going to talk about today, but there are many other such DevOps pieces that you need to put in place to actually the 2 clouds to stay in sync and then support our migration. So the mirror maker is one such component, then you had cluster link and dedicated clusters and all other stuff which is not relevant. What is important here is this real-time mirror makes sure that everything that producer writes into the topic is immediately copied to the topic to the other cloud, into the Confluent Cloud. When that is happening, then we can now switch consumer to the other cloud. So that's you see by the shift with the red line there in the middle of the migration phase. Now when all consumers are shifted, then we can easily shift the producer because they do not need to write, remove the real-time mirror, and delete the topic from the legacy cluster. Once again, this was not as simple as that. And the reason behind this, in a big organization like Helvetia, where many different teams are working in parallel, they do not really talk to each other, and there is not a lot of need to talk to each other. So they essentially create producer-consumer cycles. So a consumer is producing back to the same topic or to another topic. So just moving a consumer doesn't mean that you have also moved the producer of it. So you have multiple definitions. And I mean, that would be another talk to actually get into this. But we had a lot of issues. We just cannot do it. What we came up with instead is we are going to make our self-service support the migration itself. So we invented this migration flag, where when every stage is migrated, it will be converted from pending to complete. And that means that we have to change our Terraform script a little bit to make sure that we do not create the topic definitions before a topic is migrated, because that would be a conflict. A mirror topic cannot be provisioned through Terraform. That's how it is. If it is set at pending, then no topic is created. If it is complete, then topic is created if it doesn't exist. And if the pending is then turning into complete, then we need to do something called a Terraform import to actually bring the existing resource from the cloud into Terraform management. This was the final stone that we needed to actually be ready for migration. Now the question, how do we start? Where is the migration starting point? So we needed to do some kind of graph analysis to find out what our interrelationship is about. We did a lot of matrix analysis to get a picture of our definition space, but that was not enough. But the results were really cool. We had a diagraph generated and all that stuff. I cannot get into details about it. But what you do instead, reusing the same thing, we created a Neo4j diagram, which can be then visually analyzed. And the visual analysis of something like this looked like the following. So this is one of our clusters. You see the dots are many. But you could see there are islands, there are certain parts that you can migrate ourselves very quickly in a small batch, and so on and so forth. All of this information together lead to a final migration planning by the user, by our Kafka experts, which he then analyzed it at the application level, and then realized that in order to achieve all the goals that you want to have, this would be our migration waves. So we can split it into small groups of application and execute it over a period of time through the weeks. This happened till end of 2023, and then it was time to clean stuff up. Cleanup means a couple of things that you built was no longer needed, so it was a simple code cleanup, but we also did a little bit of optimization, because when you do two things in parallel, you create a lot of unnecessary things which you would not need anymore. And then that was it. That was the end of our migration. What we did here, during this 1.5 year of time, we built a lot of cool Elixir tools to help with the migration and analytics and statistics. There was a reporting tool. We generated the Terraform import script with an Elixir tool that actually was generated from the topics that we have been migrating. So in every wave, end of wave, we did that. And then we used an ACL comparators to find out if the migration is going right, the old set of ACLs and new set of ACLs, there is no anomaly between them, and so on and so forth. What we learned from this 1.5 year experience, that you need to maintain both. There is no negotiation about it, because users need to be oblivious to where the data is coming from. Do not worry about code getting complex, because some part you're going to delete and you'll have chance later on to clean them up. Do not try to refactor too early, once again for the same reason, that what you refactor may be deleted eventually, so there's no point. Planning ahead helps. And be ready to accommodate some requirement changes that coming in last moment and too quick. Optimize and simplify code, remove legacy, and so on, the basic software engineering lifecycle, so to speak. What you're going to do next? Performance improvement, bug fixes, obviously, but also want to improve user experience. We need to find out to prevent leakage of cloud cost, which are unused resources on the cloud, because we pay for them as long as they are provisioned, and then clean stuff up. And finally, we want to improve how the provisioning architecture works. The Terraform or some other mechanism, split them and stuff. That's, again, a topic for another talk. Thank you very much for your time. It was not an easy presentation for me to prepare.
All right, thank you. We've got time for questions. Anyone? Yeah.
Thank you for the talk. Yes, well, we could see that there are lots of work and thought put in the presentation. I was wondering if you had cases where you thought, oh, this work will take just very quick, we'll do that quickly and move on, and it turned out like much more complex than you expected.
There was many times.
Right, I see.
Many times. I mean, it would be arrogant of me if I said that I knew exactly how it's going to be or how it looked like in the end. So we started always with a prototype. Let's see how it goes. So was like the first Terraform script I wrote to actually see if I can provision Confluent Cloud was handwritten. Then I knew exactly what I have to learn and do, and then it was always like a bottom-up approach to the goal, to the solution. Yeah.
Thank you very much for your presentation. I wonder what was the reason of the migration in the first place? Like,
right.
why not moving directly Kafka to cloud if needed?
Yeah, so the reason of migration was our legacy Kafka self-service cluster was actually working quite well. There was not a lot of a problem. But it was self-hosted, which means with a small team of experts and Elixir engineers, we just could not support a different need coming from the entire organization, such as terms of scaling, more resources we need, 24/7 support, and so on and so forth. So as a policy in Helvetia, we have buy before make. So we wanted to outsource some of the support and other processes like training, project management, support, and all of that stuff. And we did this few evaluation and we ended up with Confluent Cloud. It's kind of had all the check boxes we are looking for checked.
Here's another.
Well, thanks so much for your talk. I have a question about switching off the producer from the old topic to the new topic.
Yeah.
So for some consumers, the order matters. And when you mirror from the old topic to the new one, and you switch consumer, it is straightforward and easy because the order is maintained. But when you switch producer, at which moment do you make sure that all events from the old topic has been mirrored to the new one?
Okay.
To not have a concurrency moment when you have a producer in the new topic and still some events not mirrored yet.
Yeah. So in order to know that, we had a cluster link between the old cluster and new cluster over which the mirror maker was running. And the mirror maker actually tells you where it is reading from or what is last read, and also tells what is last written. So this lag between the two offset on the two clusters was our point of determination that when we want to move it. So when we see that this mirror maker has not backed up everything, then we basically stop the producer for a moment, let it catch up, and then or restart sometimes the mirror maker. I mean, we had issues with the mirror maker. It was not as simple. We needed to restart it a couple of times to actually catch up with stuff. But that was the only way. We did not find out another way to do it.
So to build on top of that, running Mirror Maker and making this migration, let's say, complete is kind of a manual process. You have to let's say, to sit with it and see if it's actually gone through or not, correct?
Semi-manual, I would say, because Confluent provided an OpenShift operator, which is then another Kafka cluster inside the legacy, which can read from the other cluster. Now, this OpenShift Confluent operator could then run the mirror maker in an automatic way. Apart from the signals and alerts and stuff where we need to intervene, we just let it run automatically and work in 70% of the cases. Yeah. Okay.
All right, we've got time for maybe one more. Any others? All right, thank you, Bikram.
Thank you.